So hello everybody, my name is Rodrigo Gómez Vázquez. Hello from Vienna. I'm from the Vienna University of Technology, working at the research group for photonic technologies, and we are in charge of the simulation-based study for prosecuting the optimal or the tailored beam shapes that optimize the processes. You may ask yourselves, why are we in charge of this part of the project? And for understanding that, I should give you a short overview of the kind of tools we're using to work with here in the department. So we have been developing on models for the simulation of laser beam processing in general. Would say over a decade already. And the models we develop here are not aimed for laser beam welding or for laser beam cutting or something ad hoc, but we have a different philosophy that consists on trying to implement physical mechanisms mostly in form of differential equations, so that our models are actually capable of reproducing the same mechanics as the natural process. And so a short overview here. We are working with a multi-material volume of fluid approach in compressible physics and with the laser beam physics here. I think instead of paying attention to the items on the table, I would rather bring your attention to this diagram here. I think it is more human friendly to understand. So first thing we have to take care here is the propagation of the laser beam. We are not using Maxwell equations. We are using some simplified approaches, but nevertheless we can take into account the convergence or divergence of the beams, multiple reflections. The absorption is not a constant value, but of course it is something that depends on the material, depends on the polarization, inclination angle, and also on the temperature values, because the materials fortunately won't react this way. Once we extracted or we identified from the absorption the precise amount of energy that has been absorbed by the material, we can convert this amount of energy into heat, and this by means of the energy conservation. We have heat conduction and heat convection. Here we will see some the materials will heat up, and depending on the magnitude of this overheating, they may even eventually experience some phase transitions, being that melting or even evaporation. And for sure, we deal with the latent heats that must be subtracted in every phase change or added in every phase change. This is something really challenging in this kind of simulations. And for sure, once we have molten different fluid species, molten species in contact with gaseous species and different temperatures, we have to track the free surface, which is continuously evolving. And for that, the use of Navier-Stokes equations is and combined with volume of fluid is something very useful. But instead of talking further, I think an example is much better to understand. So what you can forget what I already mentioned. So that's here you can see the substance. It's a real case scenario of laser beam welding for keyhole welding conditions. That's an aluminum alloy, a low alloy aluminum with certain process parameters that have been chosen in order to show some interesting behavior of the material. And the interesting thing here is, despite of having some symmetry conditions, so we are not simulating just one half of the problem. We are simulating the whole problem. We don't suppose symmetry. But I can tell you, we are just moving a straight path with constant power and constant movement, and nevertheless, the reaction of the system, the response of the system, is not steady. Is not such that reaches a steady state. It's something oscillatory instead, and you can see. Mainly due to this negative focal position, which is inside 2 millimeters below the surface, you can see that the process becomes unstable, and we have continuous spiking due to the excessive evaporation and moving the melt path, and also we leave sometimes some pores behind where and they used to be at the parts where we had the spikes, and sometimes you can see also some sputters being ejected. So you can see the kind of complexity that needs to be taken into account for reproducing a real laser process like this. On the top, you can see some comparison with experimental results. The reason why the spikes are not so resolved in the simulations is that was a 60 millimeter weld bit, and we couldn't afford that time for finer mesh elements in order to have finer resolution. But nevertheless, I think the results were, if you see this, and they are more than reasonable. That was just one example for laser beam welding. But as I mentioned, we didn't develop a model for laser beam welding. We developed a model for laser beam processing. So we implemented the physics of laser beam and phase transitions and so on. So we are also working, or we also have experience with remote cutting processes, or with pulse ablation, like scribing, drilling, both on pure materials, metals, but also on semiconductors, on dielectric, semi-transparent materials, and even with ultra short pulse induced microstructures. And so, by the way, if you're interested on more details about the simulation I showed, or seeing just the fancy colors, you can go to our YouTube channel there. Just look for laser-assisted manufacturing, and you will find some interesting links that are more representative of the kind of work we perform here. And in the description, you will see some reference to the relevant papers as well. So let's come now to the topic. So for the purpose of custodian project, in terms of simulating laser beam welding, we didn't need to do much extra work here. So the model was already well established for joining processes by the time of starting this project. It's more a matter of validating the input properties, which are mostly unknown, especially for the high temperature ranges. You just have to make adjustments by means of experimental verification. In the case of powder-based additive manufacturing, laser powder bed fusion, it is a bit different, the story. So we are following two different approaches. So ideally, I would rather prefer the mechanistic approach, because resembles more accurately the mechanisms that the real process has. Like having a block and a powder bed or layer of a certain thickness composed by actual powder particles. That's something challenging, because we mostly work with mesh-based models like volume of fluid and finite volume, and this is you need a very, very fine resolution in order to be able to simulate domains that are representative enough for attaining the heat accumulation effects. And that's why we have a second approach that uses the concept of porosity in the layer. We try to put the volume of fluid layer at the top that which physical properties are adjusted to resemble the absorption, the heat conduction, and so on of the actual powder. You can see here an example or in action booth approaches for just some reference conditions we have for laser powder fusion. At the left-hand side, you can see the mesh-based approach, which is much more efficient in terms of simulation time. I think this 6-pass simulation for a single layer took like a couple of hours. The right-hand side, you can see that simulation. The video takes longer, but this is not related with the simulation time. But the simulation actually took longer because we had to generate the powder bed with Lagrangian particles that are meshless methods, so they're like single bolts or single particles, and we had to couple both approaches, Lagrangian and Eulerian approach for mass transition and energy transition and momentum exchange during the whole process. Some interesting things that we can envisage once we have this ready is the study of mechanistic processes like denudation or even the wetting of the particles. And the good thing of using Lagrangian particles instead of mesh-based method for the powder bed is that they are relatively cheap in terms of computational demand. And so we will be able, even if this domain is small, we will be able to perform simulations with much bigger domains, like 10 millimeters times 10 millimeters. Additional extensions that we are foreseeing here and that we are also carrying out is concerns the solidification prediction characteristics. We are working on the integration of a solidification software called SPRIME in order to be able to reproduce the grain growth physics in the solver, because our solver can produce a great output regarding the thermal fields, and this is exactly the input that such kind of solver would need. And as Mauricio mentioned before, knowing the grain structure, you already have one part of the way walked. Something which is a novel approach from us in order to be able to assess not only the thermal fields but also the coupled effect of thermal fields and thermal induced mechanical strains is variable density solid phases. So that the density of the solid phases changes with temperature, and that way we can use the values of the pressure as a kind of rudimentary way to understand better where can we expect high deformation stresses or high thermal induced stresses and where not. Sorry. So and regarding the search for the tailored beam shapes that can help us to optimize the process, we need to take 3 points into account. First, we need some initial reference conditions. So we need to define which is our starting point. Once we know the starting point, we need to define an objective function. And with that, I mean, where do we want to go from this reference point? Do we want to be able to perform the process faster? Do we want to reduce the cooling rates? Do we want to whatever? It doesn't have to be a unique objective function. We can also simultaneous objectives, but it makes the problem more complex. But it's in principle it is possible. And for the optimization, and that's what I mentioned here, the third thing we have to take into account is optimizing consists on finding a local maximum or local minimum of something, but you have to put the borders of your study, and these borders are established by the technological limitations. For example, the available power of your system is limited. Your application may induce additional restrictions like lateral symmetry or things like that. Your optics may not be able to perform whatever fancy beam shape you may think can be optimal. So we have to always keep in mind what is possible, which is our window of possible variations. the whole time. An additional restriction we wanted to establish here is, in order not to change the reference condition, we wanted to maintain and change also the primary beam. What we call the primary beam is just the red spot in the middle, which is like the beam which is responsible for generating the reference conditions that are to be optimized. Here you have an example, a very simple example of laser beam welding of stainless steel. There are two plates of 1 millimeter separated by 0.4 millimeter gap with some successful conditions to join them together. But just as an exercise, imagine we want to ensure full penetration and increase the joint width, which is also good for the stability of the process in the industry environments and for ensuring also the mechanical resistance so just what we see here is just a dummy example using a two-spot combination. I'm not going to enter into the details of the shapes of the two spots, but you can see the scale, the emissivity, which is nothing else but the fourth power of the temperature here as a rough simplification, in order to see the difference in the thermal field that originated that different result. For the case of powder bed fusion, here's just also a very simple example in order to explain what kind of work we are doing, trying to estimate here the impact or the effect of different variations in the beam shapes on the final process. You can see here also comparison of of the reference conditions, again, conditions using a Taylor beam. And that what we can see at the right-hand side is just a plot along the white line in the symmetry axis that shows that we indeed can obtain, we have some space for optimization of the cooling rates here, which is actually what we are prosecuting. But in reality, the process is a bit more complex because, as Mauricio mentioned before, we are not talking about a single point or a single track or not even single layer environment, but we have several passes, several layers. So we have to go to 3D, and so we have to deal with this kind of graphs that in order to explain you. So we are just evaluating some similar plot of the thermal history of the maximal cooling rate experienced by every single mesh element in the 3D volume. And the idea is to bring these belts towards the minimum values of the maximal experienced cooling rates in order to reduce these solidification problems. So thank you very much for your time, and I'm open to your questions either yet or later. I will be glad if you want to contact us for with any issue you want to discuss. Thank you.